One can categorize kinematic constraints in different ways. Here, we're going to talk about holonomic versus non-holonomic kinematic constraints. Now, a constraint is holonomic if it can be expressed as a function that depends on position variables and time, although it doesn't need to have time in there. So in other words, you must be able to write the constraint in the form f x1, x2, t equals 0, where again, these x1, xn, x2 terms, these are position variables. For instance, maybe they're x, maybe they're a y, maybe they're an r or theta or something like that. And what's important is that none of these terms here depend on velocities or any other higher order derivative with respect to time. And so we call a constraint that cannot be written in this form here, we simply call that non-holonomic. So any constraint that is not holonomic as said in the name. In this course, we only have and will continue to consider systems that have holonomic constraints. Let's return to our rotating or pivoting rigid rod example. So again, our rod can rotate about this pivot point here. Now the constraint that's imposed by this pivot point is holonomic, and that's because I can write that constraint as a function of position variables, which in this case are x and y. So I can use variables x and y, and I can use that to describe any point on this rigid rod. For this example, I'm just going to put P, use point P here. So the constraint equation that's imposed by this pivot point is as follows. Say the length of this rigid rod is L. The constraint equation, so constraint equation is x squared plus y squared equals L squared, or just rewritten a little differently, x squared plus y squared minus L squared equals 0. And this comes from the Pythagorean theorem, right? And so with this equation, what we're saying is that the positions of x and y, or the values, actually depend upon one another. And so this equation not only says that they depend upon one another, but it describes how they relate to one another. And again, if you go back to our definition of a holonomic constraint, right, it has to be a function of position variables. It can also be of time. It must then equal to 0, right? So this equation here fits this form. Now, you may be wondering to yourself, okay, that's true. I understand that this constraint equation holds for this rigid rod example here. However, you may have also thought to yourself, I've never actually wrote this equation down when I was solving problems that had, say, either pendulums or rotating rods before. Don't worry, in one of the following videos, we'll go over how you've actually been implicitly considering this constraint equation all along without actually writing it down. But before we move on, you might also be wondering to yourself, what is an example of a system that has non-holonomic constraints? Well, systems with non-holonomic constraints, they can still move to any point or configuration in a 2D plane, but the direction of their motion is limited. So an example of such a system is your car. So here's a top-down view of a car. Your car can be put in any configuration, right? I can put its center here and orient it here. I can get it to this configuration over here. However, you cannot necessarily get to certain configurations by moving in a certain direction. So for example, if I wanted to take my car here and I have, say, I want to parallel park it, there's two other cars here, I can, of course, get my car, usually, if I do it right, can get it into that configuration. However, you can't get to that configuration by moving sideways. So in other words, there is a non-holonomic constraint, and that comes from the fact that the direction of movement in your car is limited by the wheels. So if you can't parallel park, don't worry, it's not you, it's your car. And again, just to reiterate, the only systems that we have and will continue to consider in this class have holonomic constraints.